Thank you very much, Professor Andren, for introduction. Good afternoon, everyone. So this talk is exactly about this mysterious phenomenon. However, in order to, before getting to all details of this process, it requires some prerequisite. The bipolar pure process, well known for its interesting practical related benefits. However, it has a serious drawbacks, mainly associated with its complexity and optimization of the process. Without negative pulses, simple anodic unipolar process is characterized by a relatively simple breakdown type current response, both in upward and downward direction, and we can see usual microdischarges. However, if we apply negative pulses, the positive pulse experience a characteristic hysteresis, which, if the negative current is enough, the process turns into so-called soft sparking mode. Such processes are usually characterized by the ratio between negative and positive currents, and this is one of main parameter. Here you can see an example of three processes when positive current is higher than negative, when they are equal, and when negative current is higher than positive. And as a result, you can see three characteristic micro-discharging patterns like micro-arcing, soft sparking, and mixed behavior. Of course, the coating microstructure also differs depending on the particular positive and negative current ratio, and this is a quite powerful tool to control the coating morphology and final quality. Our working hypothesis is based on the switching between different energy dissipation patterns from columnar pattern. When original non-uniform current density reach the barrier layer, it results in localized breakdowns with so-called like vertical or columnar energy dissipation, whereas application of negative pulses results in a partial hydration of the barrier layer, which intercalated part serves as a current redistributor, resulting in a columnar or in a planar energy dissipation pattern. As a result, we have a soft sparking phenomena and much smoother interface between metal and the coating. So in first case, you can, sorry, I didn't turn. In first case, the pattern is quite wavy, whereas in soft sparking, it's almost smooth. I will not go into deep details of memristor's physics. What is useful for us that Strukov suggested quite simple two resistors equivalent circuit to explain oxide-based memristor behavior based on doped and undoped parts. And this structure is quite similar to what we have suggested before for our active zone modification. Yeah, if you consider this thin and turn it 90 degrees, we will see that intercalated part may be considered as doped oxide and undoped oxide, respectively, for other part. So having this model for the intercalation and deintercalation, we also should consider an alternative way, because we don't know exact mechanism what is going on in the pure coating at the moment. So we also have to consider the mechanism based on change in the concentration of the dopant at fixed the interface. And of course, we will have two different equivalent circuits for such processes. Having them and have some assumption on the kinetics of this process, which is supposed to be a diffusion, we can calculate an electrical response for mechanism based on concentration. The current response for such resistive network is represented by a peak between almost constant voltage range with variable magnitude as a function of the dopant concentration. And if we consider interfacial migration, the response shifts toward a higher voltage. So such a different responses should be distinguishable in experiments. And in order to verify this, we designed following complex electrical mode, which comprised working pulse train. It's a regular trapezoidal 50 Hertz and 1.3 current ratio pulse train, followed by a diagnostic pulse train the core of which is the potentiodynamic triangular pulse, which is characterized by the difference between upward and downward current. And the difference between them is so-called a hysteresis current, and corresponding charge of this current is the hysteresis charge. And between the working pulse strain and the voltammetry potentiodynamic pulse, we introduced a few variable pulses with various magnitudes. Simple silicate alkalite electrolyte and typical current density were employed. So if we look into experimental results, when we vary the magnitude of the negative pulse preceding potentiodynamic, we see that the hysteresis current response changes progressively, increasing. If we introduce intermediate positive pulse and increase it step by step, we see how the current response, the hysteresis current of the process, shifts to the higher voltage range. If we compare with what we expected from the modeling of the resistive circuits, they are quite similar. So we can assume that negative current is responsible for intercalation via concentration-based mechanism, whereas positive pulse is responsible for deintercalation via interfacial migration. So the intercalates are like so-called pushed out from the coating in this situation. Here is the animation illustrating this approach. So under cathodic polarization, the part of the oxide is intercalated by hydrogen, which increases its conductivity, and the following positive pulse applied to the narrowed undoped oxide, which dual heating of anodic oxidation results in pushing out of the intercalated hydrogen species, and so on. Important additional information about why the diffusion is the main factor here is the process's comparison for plasma electrolytic oxidation in proton-based and deuterium-based electrolytes. And in case of deuterium, because of higher molecular weight, we can see that soft sparking is achieved a little bit earlier because outward diffusion should be a little bit slower in this case. So here is an example of various weird patterns. So here you can see how they are progressively moves around the relatively long wires, rings, or mesh, and it is known that it's much easier to initiate such process on the samples with relatively high aspect ratio. However, they can be also sometimes observed on relatively flat and bulky samples. Spatial-temporal instabilities in electrochemistry are relatively well known, and they're usually associated with N or S-type negative differential resistance features in the electric double layer response. As a result, there may be some sort of oscillations or wave propagations in such system. However, we are not going to go deep into details of those particular. What's about the peer? In plasma electrolytic oxidation, we also can distinguish S-type instability processes. First of all, this is the breakdown of the anodic film. So those processes are characterized by self-acceleration. So the higher current goes. As another example is the cathodic current, when previous cathodic current affects following cathodic current by easing its flow. As we have the situation when one electric field corresponds to a couple of real current densities, this system tends to filamentation. And this is exactly what we can see as microdischarges in this situation. The N-type behavior associated with negative feedback or self-suppressing processes can be shown as anodic oxidation when following layers of oxide prevents further development of the coating because they block current further and further. Another example of negative feedback processes or N-type instabilities is hysteresis, characteristic hysteresis for soft sparking PR processes. And in this situation, we have one current density which corresponds to a couple of electric fields, and the system is characterized usually by layering, which exactly we can observe as a layered structure of the PIA coatings and uniform growth of barrier anodic layer, which also can be considered as a layer. However, known in conventional electrochemistry, oscillations and instabilities are mostly associated with reversibility within the negative differential resistance region. However, in case of PIA, once we achieve a certain point within the NDR region, the following: if we reduce the voltage, the process will not increase the current. The process will be just shut down because we have consumed all previously intercalated species responsible for this peak. However, if we assume, and we have like one-dimensional irreversibility, and process cannot oscillate in this situation. So, however, this can be overcome if we consider different spatial locations corresponding to a different degree of intercalations. And in this case, if we start even with low current within the NDR region, we formally can move along the surface and provide increase of the external current density. So we formally can reach some sort of negative differential resistance in this situation. However, only coupled with the spatial migration. Our working model includes this configuration. So we have primary electric field distribution as a non-uniform because of some fluctuation of the control electrode position or any specific shape of the specimen. And depending on the heat developed in the coating because of Joule heating because current is going through the coating, we can consider various ways of the intercalate eliminations. This process has been modeled using CAMSEL multiphysics packet, and you can see that starting with uniform and one point of concentration, the temperature has a localized peak. Then it splits into two current peaks, and the temperature areas propagates away from the original point. And this is exactly what we can observe in experiments when one active spot is split and moves away from each other into opposite directions. Another important thing that before we considered PIA coating as a response to a step of voltage. So we considered the basic principles. However, in the real PIA process, we apply series of pulses, and we have to consider how they are working there. So we have two processes, intercalation of the coating during negative pulse and the intercalation under positive pulses. And we can see that the degree of intercalation may increase and decrease within this. However, the particular behavior of the intercalate concentration may be quite different. For example, if we have relatively low negative current, the intercalate concentration is oscillating around certain constant relatively low level. However, when we increase the magnitude of the negative pulse, the effective concentration of the intercalate may increase to a certain much higher level, and the process can be characterized by the average level of those intercalates. As a result, applying relatively fast pulses, even 50 Hz is fast enough, because we know that soft sparking can be achieved within a very wide frequency range. We should work with some sort of low-pass filtering, so the coating responds to some average value of the intercalate concentration, which depends, of course, on the current ratio, frequency, and other parameters. Okay, we are about to demystify the mystery. So the process evolving from the very beginning starts with increasing of the intercalate concentration, and when this concentration reaches some critical level, the further increase results in loss of stability, some local fluctuation, which results in a local increase of current, which results in turn into local depletion. and redistribution as it was shown before. What's important here that this shape can be simply approximated by a triangle, which slopes depends on the intercalation function and the intercalation function. Intercalation function is associated with negative current, so it's proportional somehow to negative current. And the intercalation part, the red part here, is associated with the positive current density. And the slopes corresponding can be used to formalize this system. So if we have an integer number of triangles within the ring electrode, we're expecting some sort of standing wave which can be sustainable and produce characteristic pattern. So we were interested in how the processes parameter like positive and negative currents, so positive is the ratio to some starting point and the negative is represented as the current ratio, as a functions for different numbers of integer number of triangles within the ring in certain experimental conditions. And we have those set of lines. So formally we can cross them in any direction and we should see different patterns when we cross them. To achieve this in experiment, firstly, we carried out experiment for about 33 minutes in a regular steady PO process until the soft sparking was achieved. After that, we switch process into the starting point and then provide a ramp for positive and negative currents in such a way to pass the process through this yellow line, which cross all of these pre-calculated values of characteristic combinations. And what we have found is that progressively along this main process, we could find 2, 3, 4, and 5 characteristic spots generated. As you can see, those small red dots, they are not exactly lay on those pre-calculated values. However, they are quite close. And 2 other images, which show 3 and 4 active spots, can be actually considered as 6 and 7 if we assume that those spots are just couples of much smaller spots shown for lower number of those characteristic features. So in general, it can be considered like this hypothesis of active zone narrowing is quite fruitful, not only for understanding of the process, but also for the control of such interesting features. However, the nature of the active species, is it hydration or is it intercalation, yet to be clarified. Thank you very much.
Thank you, Alexei. Very interesting.